Hey guys, hello everyone and welcome to the channel. So these are single shot videos and I'm going to post these videos very frequently up till the upcoming CSIR net and gate exam. These videos are intended to give you a quality content which contains single topic in a video so that you get to know about the topic, you get a quick revision of that topic in a short span of time. Alright, I would like to thank Karthik for providing all these slides. Karthik has prepared these slides and I'm really thankful to him for providing it for this particular video. Thank you so much, Karthik. A big shout out to you. Today's video is on nuclear chemistry. We are going to take the topics, we are going to see what are the things we have to study in the nuclear chemistry in general. So we'll cover all the basic important things from nuclear chemistry in this video. So stay tuned for that. And now without wasting any time, let's continue with our video. Alright, so nuclear chemistry basically covers two parts. One is your nuclear emission and the other one is nuclear reaction. So the complete nuclear chemistry is divided into these two sections. Nuclear emissions are those type of reaction in which you can see that an unstable nuclei is going to give you a stable nuclei by emission of a certain nuclear, or you can say radioactive element. It can be alpha particle, beta particle, or gamma rays, or any kind of rays it is going to emit, and it's an example of your nuclear emission. Whereas nuclear reactions is when there is a target nuclei and there is a projectile, they collide with each other and they give a new nucleus, and along with that they give a ejectile. Okay, ejectile is what you are going to get, like what the projectile is going to get converted into. So these are the two differences between nuclear emission and nuclear reaction. Some important point which you need to know is that nuclear emissions are different from nuclear reaction. As I already told you, nuclear emission happens in degradation of an unstable nucleus into a stable one by emission of a nuclear particle. Nuclear reactions, we project a projectile on the target and we can get a new nucleus and an ejectile is obtained. Activation energy is zero in the case of nuclear emissions, whereas non-zero in the case of nuclear reaction. This is very important point, you need to remember this. Okay. Next, let's talk about some nuclear emission. So, what are the things which we need to study for nuclear emission? We have to study disintegration series, we have to study some theories of stability, and we have to study kinetic analysis. The possible emission, like during emission, what are the possible nuclear particles which you are going to get? They can be either beta particle, that is -1 beta 0. It has mass number of 0 and atomic number of -1. Alpha particle, which has a mass number of 4 whereas atomic number 2. These are actually helium particles, or you can also call them as completely ionized helium. You also have positron, which has atomic mass of 0 whereas atomic number of +1. Gamma rays, which does not have any mass or any like atomic number. Neutrons, where the mass is 1 but the atomic number is 0. And the last is electron capture, where this is actually same to what you have as a beta particle. Just the way how they are represented is different, but the particles are same in both the cases. Now, something which will help you to solve questions based upon your nuclear emission is that you need to compare the mass number and atomic number of the nuclear emission reaction on the both the sides, and it should be equal. Okay, so on both the sides, your mass number and atomic number should be same, and this should give you an idea that how many particles are going to emit, which particle and how much of them are going to get emitted. So it's just a tip to remember. Now there is a table which helps you to understand that what does this particle do. This is neutron to proton ratio, then this is group displacement law, and then there is a relation. Now what does this group displacement law tells you? It tells about that how the element is going to shift in the periodic table. Okay, or you can say basically that how the atomic number is going to change. So right shift means it is going to increase and left shift means it is going to decrease. Okay, so as it is said ki GDL means group number in the periodic table. So how the group number is going to change. Okay, so right shift means if this is the periodic table, these are the like say groups. So if right shift means if something has shifted from here to here, that means a group has increased and it is shifted by right. So when it will be done when the atomic number is going to increase by 1 unit, right? So this is how it is done. So a beta particle decreases the n by p ratio and it gives a positive, or you can say a right shift of 1 unit to the group displacement of the system. and the relation should be isobar. What does that means? It means, let's say if you have some element X which has atomic number A and mass number M, and if it gives a beta decay to give some compound Y with a beta decay which is having atomic number -1 and 0. So this Y will have a increase in the atomic number by 1 unit. So A plus 1 will be the atomic number of it and mass will be M. So that's why in the group, if it is somewhere over here, so it is the atomic number has actually increased. So it will give a right shift in the group. I hope this is clear. Then for alpha particles, they are going to increase the n by p ratio and it will give a left shift by 2 units. Simply you can understand it in this way. Let's say if same element X with A and M, if it is giving a alpha particle decay, in that case the compound which it is going to form Y should have 2 less atomic number. So the atomic number and the mass number is also going to decrease. So atomic number will decrease by 2 unit and mass number is also going to decrease by 2 units. So it will be shift towards the left side in the periodic table. Next is positron decay. It also increases n by p ratio and it gives a left shift by 1 unit. And what is the relationship between the reactant and the product? For beta particle, they are isobars. For alpha particles, they are called as isodiaphers, means number of neutrons are same over there. And in the positron decay, the elements which you get, they are also called as isobars. In gamma rays, there is no change in n by p ratio. There is no change in group displacement law. That is, they are not going to shift anywhere. And these are called nuclear isomers. They are different in the quantum energy level. That's it. The next is neutron decay. In that case, the n by p ratio decreases. There is no shift, although in the group or in the atomic number of the element, and these are called isotopes, means they have same atomic mass but different masses. Sorry, same atomic number but different masses. And the last one is your electron capture, which actually increases your n by p ratio. It gives a right shift by 1 unit to the GDL, and these elements like the reactant and product are isobar of each other. So this table will give you a short idea of how the things are related in a nuclear emission reaction. Okay, as I already explained you about this, that what is GDL and alpha particle, they just give a left shift by 2 unit. This does not happen in lanthanides and actinides. So lanthanides and actinides does not give alpha decay. This thing you should remember. Okay, theories of nuclear stability. The first theory which we study for the nuclear stability is called stability belt theory or n by p ratio theory. What does it say? It says that for atomic number less than 20, your n by p ratio should be equal to 1. Whereas if you go atomic number greater than 20, the n by p ratio should be somewhere equal to 1 by 5-2. Okay, that should be the ratio. Otherwise, if it is not followed, then the nucleus is said to be, or the nucleus of the molecule is said to be unstable. So the element is unstable if it does not follow this stability rule. Also remember that for atomic number more than 83, there is no stable nuclei which is present. Now this can be easily illustrated from this diagram or from this graph. The atomic mass is given over here, atomic mass, and where n is neutron, and here you have atomic number. So the ratio of both of them, you can see this dotted thing which you can see, this is actually the stability belt, and this straight line is telling you n is equals to z, that is 1:1 ratio. So it is the stability belt is following this 1:1 ratio up till 20. That's why it is said for 20 and less than 20, n by p should be 1. When you go beyond 20, it is shifting or it is moving away from 1. So it's increasing. The value is 1.52 somewhere. Whereas if you go beyond 83, so there is no stability belt lying in this region. So that's why it is said that there is no stable nuclei after that. So it is just illustrated over here. Alright, the next theory is called meson theory. Meson theory are like, mesons are basically charged particle. They are interconvertible neutrons and protons by pi meson. So basically pi mesons are the thing which can convert neutron into proton. So if a neutron captures positive meson, in that case it will get converted into proton, whereas if a proton captures a negative meson, it converts itself into a neutron. So this is given by the meson theory. It's basically given to understand how neutron and proton are interconvertible among each other. So the next is even and odd theory. What it says that if you have even number of proton or even number of neutron, in that case there are more chances of stability. There are 165 stable nuclei which have even proton and even neutron. Whereas if you start making things odd, let's say protons are even but neutrons become odd, in that case lesser number of nuclei are stable here now. and if you make protons odd and neutrons even, then even lesser number of elements are stable. And if you make both the things odd, then very few elements are stable with odd number of proton and odd number of neutron. Now you guys have to tell me in the comment section one example where you have odd neutron, odd proton and odd neutron, and still the compound is stable, or still the element is stable. You guys have to tell me in the comment section name of one such nuclei. Okay, the next theory is of magic numbers. So there are certain numbers like 2, 8, 20, 28, 50, 82 and 126. These number of neutrons or the number of protons or both makes the nucleus exceptionally stable. This is nothing but just a experimental data which is considered as magic number over here. So that's what it is. So if the element, or if the nuclei has 2, 8, 20, 28, 50, 82 or 126 neutrons or protons or both, in that case it will be more stable than the others. So most decay series stop at lead, that is 208 Pb82. This is the value where most of the decay series means if you start from uranium 235, let's say, so it will keep on getting decayed at the end. When the lead 20882 is reached, at that place it will not decay further. So it's a stable nuclei because it has magic number of neutrons and magic number of protons in it. The next topic which we have to study is binding energy of nucleus. Now this binding energy of nucleus is when the free neutrons and protons are bound inside the nucleus, there is a mass loss, or you can say there is a mass defect which is there, and that mass defect is given by delta m, and delta m is equal to theoretical mass minus the actual mass of the compound, and binding energy is equals to that mass defect multiplied by 931.5 mega electron volt. Nuclear stability is calculated by dividing this binding energy with the number of nucleons which we have. So this value is called as binding energy per nucleon. Okay, this is called binding energy per nucleon, or you can also divide binding energy with mass number, but binding energy per nucleon is more standard way of understanding the stability of nucleus. So more binding energy per nucleon, that means more stable the nucleus is. Thus iron 5626 is the thermodynamically most stable nucleus. So if somewhere it is asked which among the following is the most stable one, what you have to do is you have to check out the binding. First of all, you can simply check out the magic number. If they follow magic number, they will be more stable. But if you find out this iron 5626 isotope of iron, this is going to be the most stable nucleus in the whole periodic table. Next, let's talk about some nuclear reactions. So radioactive processes are always of first order. They follow the first order kinetics, and the rate law for them is given by n is equals to n naught e to the power minus pi t. Okay, you can also write it down in the form of, just like you write down for the first order reaction, that n is equals to n naught e to the power minus kt. Okay, now what are n and n naught? So n is the number of radioactive nuclei at some time t, so at some final time t. N naught is the number of radioactive nuclei at some initial time. Pi is called as your disintegration constant, just like rate constant you have in the chemical kinetics, just like that pi is disintegration constant. T half, that means half lifetime, is calculated as 0.693 divided by pi. Okay, pi is working as the same as how this k works for the chemical kinetics. Number of radioactive nuclei present after n number of half-life is equals to this. So this is the formula, n is equals to n naught divided by 2 to the power n. This is the formula which you can use if the question is asked that, let's say, tell the number of radioactive nuclei after 5 half-life times. So n will be 5 here. Initial concentration or initial value of nuclei will be given to you, and that's how you can calculate. Next formula is for T average. So T average and T half can be related with each other. T average is the time required for average decay. Okay, so T average is equals to 1.44 multiplied by T half, or you can say T average by T half is equals to 1.44. Unit of pi, this is very important. So 1 dps, dps is decay per second. Okay, this is decay per second. So 1 decay per second is equals to 1 becquerel. Okay, this is becquerel, and this is equals to 10 to the power minus 6 RF, that is Rutherfords. So 10 to the power minus 6 Rutherfords, or it is also equal to 1.27 into 10 to the power minus 10 Curie. Now this thing is going to help you mostly for your GATE exam, like wherever you have to change the units from decay per second to becquerel or to Curie. This is how you are going to use, and that's how you are going to change it. Effect of temperature on the disintegration constant. So let's see how it affects. So it is similar to what Arrhenius has suggested. It is going to get affected in the same way. So we have studied that K is equals to A e to the power minus EA upon RT. This is what we have studied in chemical reaction, or basically in kinetics, what chemical kinetics, right? So that's what we have studied. Here K will be replaced by pi. So pi is equals to A e to the power minus EA by RT, where EA is 0 for nuclear emissions. So that's why nuclear emissions are temperature independent, okay? Whereas for nuclear reaction, you will have some value of EA, that is for, you will have some activation energy for that, and there it won't be independent of temperature. So remember that this formula is for nuclear reactions, nuclear reaction. And if someone is asking that how nuclear emissions are dependent upon temperature, the answer is that they are independent of temperature. Alright, the next thing is about nuclear reaction. So if there is some reaction, that is T plus P giving Y plus E. What are these T, P, Y and E? So T is the target, P is projectile, Y is the yield which you are getting, and E is your ejectile, okay? So it can be written as that T, P comma Y is equals to E. So what does that mean? It means if I write down a reaction or nuclear reaction like this, let's say I have nitrogen 714, and if I am writing it like this, that it's getting electron capture, and this is giving me carbon 6 and 12, right? And along with that I'm getting some, let's say, gamma particle. So how I'll write down this whole thing? I will write down it in this way, that N714 is, and in the bracket I will write down E minus 10, comma, I will write down here gamma and C612, okay? So this is how you write down nuclear reaction. This is the representation which you use to do it. So EA is not 0, thus Q will be the released or absorbed energy, okay? So Q will define the energy which is released or absorbed, because here in the nuclear reaction activation energy is non-zero. So when the mass of reactant is more than mass of product, energy will be released, and those reactions are called as exoergic reaction. Here Q will be positive. Whereas when the mass of the reactant is less than mass of the product, then energy will be absorbed, and these are called as endoergic reactions, and in this case Q will be negative. Now Q will be different from thermodynamic one, so don't confuse this Q with the thermodynamic energy, okay? So this is the amount of heat which is released or taken during this particular reaction, and this depends upon the mass defect or mass difference of the reactant and the product side. All right. The last thing which we will study is the cross-sectional area of the nuclear reaction. So there is a formula between which relates your cross-sectional area of the nuclear reaction. On this also we have a lot of questions which have been asked in CSIR net. So R is equals to R naught A to the power 1 by 3, where R is the radius of nucleus, R naught is constant which has this value, that is 1.2 into 10 to the power minus 15 meters, and A is basically the mass number, and cross-sectional area is given by pi r square. So first thing is that you have to calculate the radius of the nucleus depending upon the mass number. So that can be easily calculated by the formula R is equals to R naught A to the power 1 by 3. So if you have to calculate the radius of, let's say, some element given, let's say for carbon, so you'll put the atomic number, the atomic mass of the carbon and R naught value, and then you will calculate the atomic radius of the nucleus of the carbon. And once you get that, cross-sectional area will be equal to pi r square. Put the value of r here to get that. One more thing, that the answer which you will get as the unit of cross-sectional area will be meter square itself. But in case if you want to convert meter square into barn, so that's also one of the unit for cross-sectional area. So 1 barn is equals to 10 to the power minus 28 meter square. So this is how you can use this unit conversion to convert meter square into barn or barn into meter square. Generally, whenever the question will be asked on the basis of cross-sectional area, they are going to ask in terms of the answer, they are going to ask in terms of bar. So you should be aware about this. So that's it for this video. I hope we have covered most of the things from nuclear chemistry. At least you will get an idea before exam. If you watch this video, it will just give you a quick understanding of the topic. You will be like, it will just give you a quick revision of the topic. And I hope you like this particular video. Do let me know in the comment section if you guys like this type of videos. If you like this content, I'll try to make more videos of this type. I'll try to make more videos frequently on this particular single shot type, so that it can help you during your exam time. So that's it from my side. Thank you so much for watching this video. I will see you guys in the next one. Till then, have a great day. Bye bye. Take care. Hey guys, so I teach live on Uncademy Plus platform. Here I teach for the CSIR UGC NET category, and you can follow me over here for regular classes. You can access my free classes as well as my paid classes on this particular platform. The classes which are free, you can get that under the section of special classes, whereas in order to access my paid classes, paid live classes, you have to take Uncademy Plus subscription. So do make sure that you take the Uncademy Plus subscription to access all my paid classes, which are quite organized. The whole syllabus is being completed over there, and the classes are quite regular over there. So make sure that you take Uncademy Plus subscription by using my referral code, that is N_Huda. That's it for this. Thank you so much.